reminders before we start today's lecture. Next week's going to be a busy week, so start preparing. May 26th is going to be the project proposal and schema due. Please have it with you, and you're going to be handing it in at the beginning of the lecture on May 26th, which is on Monday. The first phase of the project is not to mark you, but to give you feedback on whether you're on the right track or not. Okay, so a lot of you had questions about, is this big enough or is this too small, what we're having in mind? So this is basically just to give you feedback. Give us an idea of what it is that you want to do. We'll provide some feedback for you, and then for the second round, you'll be making adjustments to the actual design of the project, so then what you have in mind is close to what we expect you to do for the project. Although it's not mandatory and it's not marked, I strongly encourage you all to hand it in, because it's an opportunity for you guys to get some feedback from the TAs who will be marking your projects later. May 28th is one more thing on the projects. So a lot of you are asking about whether what you have is good enough, or whether it's covering enough things. This checklist is basically what the TAs will be using at the end in order to mark your projects. This checklist is available through the course website. If you go on projects and then completed project, at the bottom you find a checklist. This checklist is going to say that you're going to need to have a join SQL, you're going to have a division, you need aggregation, you need nested aggregation, deletion, updates, a graphical interface. So all the things that you need to have in your project to get full marks is up here in this checklist. I also have 3 points for extra features that your application supports to encourage you to be creative, to come up with other functionalities or features for your project that are not actually mentioned here. Okay, and you can think about anything that you might feel is useful. It could be the security layer, that you have different privileges for different people. It could be anything. Okay, so I'll leave that up to you to come up with some cool ideas for that. Any questions on the project? A is also attending the tutorials, so you can just have a quick talk to Paige during the tutorials as well about your project. He would probably not be able to give you, a full detailed explanation of what he thinks about the project, given there's a lot of you. But this is why we have the feedback, the schema due proposal, so he can give you a more informative feedback written. Okay, May 28th is the first question submission deadline. The form has been on for quite a bit now. Make sure that you go to the website and enter really cool, quicker questions to use in future offerings of CPS and PO4. And May 30th is going to be our first midterm. I'm still double-minded about whether we should do it here or not. I want to keep it here so then we can do part of the lecture after we finish the midterm. But then that would mean you guys will be really sitting close to each other. And I don't know how much I can trust you with that. So I haven't finalized the location yet. I'll let you know soon. It's also going to be a two-stage exam. How many of you have done a two-stage exam before? A few? So what's going to happen is that you're going to do the exam on your own first. And after that, we collect all the exams in, and then you're going to be in groups of 4s, and then you're going to do the same exam again. Okay? So have you seen how right after the exam finishes, everybody's just curious to know what other people wrote, and you're all talking to make sure you got the same answer? Well, this is an opportunity for you guys to do that exactly. The second round that you're going to do it, you're going to talk to each other, and the 4 of you together will hand in one exam. So you're going to be writing it all together.
Which copy will be graded?
Sorry?
Which copy will be graded? My personal copy?
Which copy will be graded? And the answer is both. Your personal exam is going to be 85% of your mark. your group exam is going to be 15% of your mark. If you do better on your own compared to the team, then I'll give you your own mark. So it's going to be the max of your own mark and the combination of 85% your own work plus 15% group work. The teams that you come up with is going to be optional. You pick your own teammates. And by my experience, it doesn't really make a difference. It could be a 3 or it could be a 4. There's advantages and disadvantages in both, so I don't really care if you do a 3 or a 4. Any questions? So I haven't finalized the duration, but both of them are pretty much the same length. So if you get 50 minutes to do the first exam, then you get 50 minutes to do the second one. Now you're familiar with the questions, so you don't need as much time to observe the questions, but that will give you some more time to discuss it between. Any other questions? Okay, so 2 more notes. The Friday tutorial, you're going to be working on your projects. And it's going to be optional, and you're free to attend whatever tutorial session that you like. Okay, so this is to encourage you to attend the same tutorial as your team members, so you can all discuss what you're going to be doing and finalize that so you can hand something in on Monday. Okay, so just for this Friday, it's optional to attend any of the tutorial sessions that you like, so you can be with your members. And also, we're going to be covering Chapter 19 today. We're going to be doing quite a bit of a jump to Chapter 19. And I have added questions on Chapter 19 to the course webpage as well. This is one of the hardest parts of the course. So please go over the questions and make sure that you feel confident with the tutorial. Any questions? Alright, then let's start. Schema refinements in normal forms. This is covered in Chapter 19 of the textbook in the 3rd edition and in Chapter 15 of the 2nd edition. Okay, so on our continuing saga so far, we've learned that databases are wonderful. Hopefully you all agree with that by now. And we've learned how to create a conceptual design with ER diagrams. Then we looked at how we can take that ER diagram and come up with tables with that. Now the question is the ER diagrams that we had, was it really a good design or not? Or how can we know if something is a good design? How can we make our design more efficient? Okay, so now we're going to go back and see what modifications we might need to make to the schema in order to make that database more efficient. These are the learning goals. By the end of this chapter, you can debate pros and cons of redundancy in database. There are actually sometimes some reasons in favor of having a little redundancy in your database. Provide examples of update, insertion, or deletion anomalies. We have a look at those. Given a set of tables, you have to find the functional dependencies that go in those tables. We'll talk about 3NF and BCNF as 2 different forms of normal forms that you can translate your ER models to. And you can prove or disapprove that a given table decomposes lossless or not. So we look at decomposition and joining back tables together and whether they're lossless or not. And you need to be able to decompose into 3NF and BCNF. So if none of that made sense, right, it should by the end of the chapter. Okay, now let's take an example. Imagine that we have this entity. We have mailing address for each of our faculty members. They have a name, they have a department, and they have an address. Right? And from what we know so far, this entity is totally fine. It meets all the criteria that we've talked about so far. This could be an instance that might go with that schema. So that's me. I'm in the computer science department, and my mailing location is where the front office is. So it's going to be 201-236-6 Maple. Steve is also in the computer science department. His mailing address is going to be the same. Rachel and Ed, they're both in computer science and they're going to have the same mailing address. Joel has contracts with both computer science department and the math department, so he has 2 different addresses there. Okay, so what I want you to talk about with your neighbors is, first of all, is this a good design? Is this a bad design? If it's a bad design, why is it a bad design, and how can you modify it to make it a good design? Anyone unsure about what we're doing? All right, let's start. So, anyone? Any suggestions? Yes?
I think it's a bad design.
It's a bad design because?
Well, you're using name and department as key, and you can have 2 people with the same name in one department.
So the first problem with this is, well, is name and department really a good key? Probably not. So that's why this is one reason why this is a bad design. Anyone else? Yeah.
I think, despite the fact it's a key, it's a good design because in this case you can see if the person wants to have one department.
So the suggestion here is that if we ignore the key problem for a second, the rest seems like a good design because it allows you to see if one person is in 2 departments. Okay? Anyone else? Yeah?
There's a function dependencies and mailing location. So if you're comparing 2 tuples, if the department is the same, then your mailing location is the same. So you're basically storing a bunch of information that you don't really need to. It's wasting space. So what you can do is make another table that has only department with mailing location.
So, you mentioned a bunch of things which we don't really know yet, functional dependencies. So the suggestion there is that, well, this seems like a bad design because it seems like department is already telling me what mailing location is. And with the current design, what I'm doing is I'm keeping that information multiple times. Any other suggestions? Yes?
We can use aggregation for the department and mailing location since they are like just correspond to like each department corresponds.
We can use aggregation for the department and the mailing location? We'll see more about that. So what's going to happen if you use aggregation? What aggregation is going to do is you can take 5 tuples and you can merge them into one. But if I merge those 5 tuples together, what am I going to put as a name? Right? So aggregation is a good idea, but here it wouldn't work because the names are different. And if I didn't care about the name of the people, then I could aggregate the department and the mailing location to get that information. Okay, so it seems like a bad design, and we are keeping some information redundantly. Well, might be some problems if we want to update this, if we want to insert some new information, or if we want to delete some information.
I have a question. If I wanted to draw a statement, which one, 2 lines will be doing?
Right, so I'll give you a few minutes to talk about that. Now let's assume that this is a bad idea, right? If this is a bad idea, given that I want to update, delete, or insert values into this table, what are the kind of things that might go wrong? You might want to have an example for each of these. Any questions? All right, let's see what you guys do.
You might be listening to guess.
So what would be an example of an update query which might be problematic? Anyone? What's going to happen if I want to update the mailing address?
Yeah, what's going to happen if you're going to update your statement from math department and you update it, let's say, within math department, and right now you're working in the computer science department, you change the math department and the computer science department, and you end up with 2 similar lines.
So, if Joel is not working in the math department anymore, then I would say we can just delete that tuple, Joel Math and the mathematics location, and that's fine.
But let's assume you don't know that the computer science is really bad.
Oh, so you want to update his math department to the computer science department, and now you got to duplicate.
Yes.
Yeah, that could be one update problem. The other could be, I have department computer science and mailing location a few times there. If I update 1 or 2 of these tuples and change the mailing location and not change it in the other 3, then I have a database which has which has information which doesn't go together. At the end, I'm not sure whether the computer science department is in 201, 2366 mail mall, or is it in the other location. right? So if I don't update all of those mailing addresses at the same time, then I'm going to have a conflict because now I have two different location addresses and I'm not sure which one's correct.
What if one of the profs though is in computer science but has a different mailing location because they're offset or the different areas?
Right. So the question is, what if we have a faculty member in the computer science department, but they have a different mailing location? That is something that we get back into, that here the rule could be that one determines the other. If the department determines mailing location, we'll have all these problems. If there's not such an integrity in place, then any value you can have is fine and it's not a problem. It's a good question though. What would be an example of a deletion which will be problematic? Or more than one deletion? Yes?
If you delete both the math and finance math, then you lose the relationship between the department and the organization of math. So if you ever want to insert new people that will be working in the math department, then you won't know who your math is.
Can I get your name?
Maggie.
Maggie. So, what if both Joel and Brian decide to leave the math department? I'm going to take out both of these tuples, and in the process, I lost the mailing location of the department. Right? Assume I take out both those tuples at the bottom. Then, I wouldn't know the location of the math department anymore. Question?
Are you obligated by the language constraints when you create a new entry or a table? You have to enter name, department, and mailing location?
Right.
Or no?
So if I want to add it, I need the primary key, which is name and department. That's coming up as a problem for insertion. For deletion, the problem is that if both of these people leave, then that's fine. I have to delete them from my database. And I'm losing some information that I really didn't want to lose. I'm losing the information about the location of that department, which I should have still had in there. Because I can have a department without anyone in it, but it still has an address. And an insertion department, and an insertion problem would be, what if I want to add a new department into my database that currently doesn't have any faculty members? Right? So I want to add philosophy and the mailing location of philosophy, but given I don't have any faculty members currently in that department, I can't put anyone as the name, which is part of the primary. Okay, so there are a variety of reasons why this design is not really a good design. And let's see algorithmically whether we can come up with reasons why this is not a good design. Any questions? Databases allow you to say that one attribute determines another one. And we're going to call this a functional dependency. So if department determines the address but not the name, department determines mailing address but not the name, department has a functional dependency with mailing location, but it's not a key for this schema. Here's another example. The key here is house number, postal code, and street. If you know the three, then this is your primary key for your address. However, if you know postal code will determine the city and the province. So there's a functional dependency that postal code determines the city and the province. However, postal code is not a primary key for this. It's not a candidate key. Now the question is, why would that be problematic? Okay, so more formally, a functional dependency we show it will X arrow Y, where X and Y are set of attributes, so it could be more than one attribute in each, holds if for every legal instance, if you have same values for X, so if you have two tuples that have the same value for X part of this dependency, they will also have the same value for Y. So back to our example, if you have two tuples that have the same department name, that would mean that they would have the same mailing location. Another example would be postal code functionally determines city and province if for each possible instance that you can have, always for any T1 and T2, if T1.postal code equals T2.postal code, then T1.city and province equals also T2.city or province. Okay, so if two values agree on the X part, they also have to agree on the Y part. We read this as X functionally determines Y, there's a functional dependency, or X determines Y. Now let's see another instance. Does city determine province? Yes, in the back.
No. 'Cause
Why not?
there could be multiple provinces with the same city name.
Great. Can I get your name?
Got him?
Got him?
Yeah.
So, what we had as a rule was that if they have the same value on the X part, they should have the same value on the Y part. And it seems to be true here. So whenever I have the same city, I have the same province. Okay, so this functional dependency does hold for this instance. However, for a functional dependency to be true, it doesn't have to be. It doesn't need to be true just for one instance. But similar to how the integrities were working, it has to be true in all possible instances out there. So, given that there are two Victorias, one in BC and one in Newfoundland, then really it wouldn't make sense for us to have city-determined province. Functional dependencies are not something that you can just look at one instance and know there's a functional dependency. Similar to the integrities. We couldn't just look at one instance and figure out that this is a one-to-many or whether this is a many-to-one relationship. These are things that are given to you as facts when you're designing the database. When you're told that story about what the database will look like, you'll also be told information about the functional dependencies. Any questions? Okay, so it's important. However, one thing you can do from one instance is try to see whether a functional dependency does not hold. Right? So you can validate whether it's true for this specific instance or not. For example, when I see this specific instance, I can already tell you that a functional dependency from city to province is not true. Because I can see a counterexample of that already inside this database. So I cannot come up with all the functional dependencies, but I can validate them. We can have boring, trivial functional dependencies. So we can say that if you know postal code and house, you know postal code. Right? So if I know postal code and house, I know postal code. Doesn't really seem to be interesting because I'm saying I already know this. Given that I know this, I know this. So that there are a bunch of trivial functional dependencies that we don't really care about. Rather, we're going to concentrate more on the non-boring ones and find those in our databases. Right, get your cookies out, please. Okay, do this one on your own first, please. Right, a few more seconds. Okay, so we need to convince 30% of the class that they're wrong. Talk to your neighbors. Okay guys, so since I'm going to mark you based on participation, when I'm counting down, if you haven't clicked, just do a random click at the end so at least I know that you've been participating. So random clicking. Right, good job. I think we were really good at convincing other people. Let's see why. So, I don't have any repeated values in D. Right? If I don't have any repeated values, could there be something wrong with regards to a functional dependency? So C cannot be true because all these values are different, and as long as these are different, I can't really check to see whether anything is being determined based on the value of D. Okay, so C is definitely not right. So let's look at the other ones. What about B to C? So I have two different values for, I have two 3s here, and both of these have value 4. But B to D cannot be possible because the two values I have for 3 are giving me different values in my D, which could not be true. Either both of these need to be 3.6 or both of these need to be 3.5. Any questions? Okay, so let's look at the other example that we have. Let's look at the postal code one. So this table is giving me information about address, and let's assume that we've given this functional dependency that postal code determines city and province. Okay, so now I'm not guessing this anymore, but rather I've been given this as a fact that I know this needs to hold in my database. And let's talk about the different anomalies that we talked about before with the mailing information. I'm still going to have similar update anomalies compared to what I had before. I'm keeping this information that Vancouver is in BC multiple times and Delta is in BC multiple times. If I want to do an update on the province of Delta, I need to make sure that I'm going to update all these rows at the same time, or else I'm going to have a conflict in the information that I'm storing. Insertion anomaly would be, what if I want to add to my database the fact that B6T1Z4 is in Vancouver? So it's not a specific address per se that I want to add to my database, but I just want to say this postal code is in Vancouver. Can I do that? Can I do that in this database? I cannot, because house streets are part of the primary key, so I cannot leave them empty. And the deletion anomaly would be, if we delete all addresses with B6A to S5, then I'm going to lose the information that this postal code is in this city. Which necessarily I don't want to lose. So if you compare the two examples that we just looked at, the one with the departments and the mailing address and this one, the anomalies that we're getting on update, insertion, and deletion are very similar. And in fact, these are the sort of anomalies you're going to get if you have functional dependencies in your tables that you have not considered. Okay? So whenever you don't consider a functional dependency here, you're going to get update anomalies, similar to this one because you have redundant information. You have insertion anomaly because there's something you want to add, but it's not really part of your primary key. And you're going to get deletion anomalies, which means that you delete one thing and you're going to lose some more information with that deletion that you don't really want to delete. Why am I getting these anomalies? Because the tables or the ER diagram that I started with wasn't really a good model to start off with. So the question is, can we do better? What if I store two different tables? Right? So let's have one table, where in that table I have house number, street, and postal code. And then I have a different table. In that other table, I'm going to keep postal code and the information about city and province where that postal code is. What I've done is I've taken one big table and I have decomposed it into different tables, and that could potentially get rid of the anomalies, the update, the insertion, and the deletion that I had before without me losing any information. It's important that I don't lose any information, right? I don't want to change the information that I'm storing in my database. Now the question is, once I move into these two tables, have I gotten rid of the anomalies that I had before? Let's see the first one. Let's say I want to update Delta's province. I'm going to go to Delta, and I'm going to change the province from BC to something else. It's not a problem anymore because I'm only storing that fact once. So I can't get a conflict in the information that I have. Insertion. Let's say I want to add a new postal code and say that that's in Vancouver. This is fine in this new version that I have, because I'm not going to add anything into this table, but I'm going to add the postal code, the city, and the province in my second table. And the third problem, which was deletion, was that let's say now if I delete the two addresses on the top, I'm not losing the information that B6A2S5 is in Vancouver, because that information is still stored in my second table. Yeah?
How do those two tables link together? What is the unique
That is a great question. So one thing which is important is for me not to lose any information, right? So now that I have two tables, I still need to be able to say that Main Street at that postal code still is in Vancouver, BC. How can I link those two back together? Anyone?
You can create some unique key for the series and link them as a foreign key for the first table.
So what I can do is, I can link them based on their postal codes. Right? I'm saying that Main Street is in B4, C2, and 1. What I can do is then I can link these two back together based on the postal codes to know the city and the province for that postal code. Did we lose any information? Not really. In this example, there's no information lost compared to what you had here. All the information that you get from this table, you can also get from this table. Are our problems fixed? We talked about the three that were fixed. Do we have any redundancy? Well, we're keeping postal code twice. But this is as good as we can do, right? Because I need to have something on this side and on this side that allows me to put these back together. This is the redundancy that I have. Rise to conflict of information. No. I can change the postal code on this side, and that's fine. Now I'm saying that this house is in a different location. I can change the postal code on that side. That should also be fine, as long as I know what I'm doing. I can have an integrity, a foreign key integrity between these two that will not allow me to make that change. But if I don't have that integrity in place, making changes to either of these is fine. Question?
Could postal code also determine street?
So the question is, could postal code also determine street? If I was given that information when I was doing my design, I would have made a different design. So the reason why I have those two tables the way I have it is because of the functional dependency that I was given. If this dependency also said street, then I would also take street to the other side. Good question. Any other questions? Okay, so that worked pretty well. But the question is, how can we use functional dependencies in general to decompose our tables to get rid of some of those anomalies that we had before? Functional dependencies tell us where we're storing redundant information. Question, if I don't have any functional dependencies in a table, am I storing anything redundantly? If nothing determines anything else, then really there's no redundancy. When I have something determining other thing is where I start having redundancies. If I don't have any information about what goes with what, then any information that I'm storing is factual for me to have and it's not redundant. And again, we like to split apart our tables in a way that we're not losing any information. And so we're going to see examples of bad ways of decomposing a table in which when you put it back together, there's some information which was lost in the process. Some functional dependencies may be explicitly given to you, like the one we had here. This is something that's being explicitly given to us. based on some of the functional dependencies that are explicitly given to us, it might be the case that there are some implicit functional dependencies that also come with them. A reminder on keys. A key is a minimal set of attributes that uniquely identifies a relation. So, given that it's minimal, what we mean is that you can't take anything away from this key and for it to still be a key. Just a note that I could have minimal keys, which is 2 attributes, and another key which is 3 attributes. That's fine. You can have a 2-key attribute and a 3-key attribute and they're both minimal. So the fact that they're minimal doesn't mean that they're as small as possible, because one is now 2 and one is 3. What it means is that you can't really take away anything else from this in order to keep your key. And a super key is a key which is uniquely identifying the relation, but it doesn't have to be minimal. So a key is going to be a subset of your super key. Right, do this one on your own first copy. Right, let's finish the first round up. 5, 4, 3, 2, 1. Random clicks. Right, we've got some convincing to do.
No, it wouldn't be a minimal. I guess so.
Yeah. I was like, that's what I was like, wait, there's no. I chose the closest one. Because you only need dependency,
Right, a few more seconds. 5, 4.
no, this is like the title.
One. Hey, so some of you should have been lawyers instead. Pretty good at convincing other people. Okay, so let's look at different examples. know D determines A, B, and C. So that means if I know D, I know D itself, and I know A, B, C. So D is the key. That would mean BD is a super key because it's not minimal. Because I can take away that B, and I can still determine B based on knowing B. Okay, so these are the two that you were going for at the beginning. That's why none of the above is the correct answer. Why is not B a key? Because if I know B, B will allow me to know C, but I can't know A and D. If I know C, that would mean I know B, but I wouldn't know anything else. Okay, so E, none of the above is the correct answer. Yeah.
Maybe you're about to get to this, but I'm just wondering, what is the point of a super key?
The point of a super key is when we get into normal forms B, C, and F, and 3 and F, super. We're getting there. Any other questions? Right, do this one on your own. Three, two, one. Okay, so 35 of you are wrong. Talk it over.
At least you should try to convince others. Okay, so 6 of you are forgetting to click, but okay. Okay, so we did well, not as good as last time. Second round, first round. So super key could be, super key is a subset, and it could actually be the key itself of a minimal key. Okay, so here I know that D is a key. It's a minimal key, right? So anything added to D is also going to be a super key. So D on its own is a key and a super key. BD is a super key, and BCD is also a super key. So since D is a key, all of the answers are super keys. Any questions? Okay, so functional dependencies and keys together. So I have a bunch of keys for you. I have Alan Keyes, who's a politician. We have Alicia Keys. We have Evelyn Keyes, she's most well known for playing Gone in the Wind. And we have Francis Key, a lawyer, also wrote the current US national anthem. Okay, so a bunch of keys as well. A set of attributes determine other attributes. So A, B could determine C, means that if I know A and B together, that determines C. And a super key is the one that we just looked at, that it doesn't really need to be minimal. Okay, so this is what we know so far. Now, given a set of explicit functional dependencies, how can we determine other functional dependencies which are not given? And we can look at deriving additional functional dependencies with some rules. Okay, so the following are some of the rules that you can use in order to come up with new functional dependencies. Assuming that you know that student ID gives you city, and you know city gives you area code, you can put these together and imply that student ID gives you a code. Right? Student ID gives you city, city gives you that, therefore student ID gives you a code. Transitivity. So the three rules that you can use in order to do proofs on this are the Armstrong's axioms. Given that x, y, and z are set of attributes, you can use reflexivity. If y is a subset of x, that means x functionally determines y. So if I know city and major, I know city. These are the boring ones that we talked about. Right? Given that I know some information, I know part of that information. Augmentation says that if I know x determines y, I can add any number of attributes to both sides of that dependency. So I can add a set of attributes z, both on the left-hand side and the right-hand side, and that would mean that xz determines yz. So if I know student ID gives you city, then I know that student ID and major gives you city and major. Okay, and transitivity would be if I know x gives you y and y gives you z, then I know x gives you z. So that's the first one with it. If you know student ID gives you city, city gives you area code, that implies that SID gives you area code. Any questions about any of the rules? Based on these three, we can come up with additional rules. We can also prove union, that if I know x gives you y and x gives you z, that means that x gives you the union of y and z. So if I know SID gives you area code and I know SID gives you city, then I can put these together and say SID gives you area code and city. And I can also decompose. If I know x gives you y and z, I know that x gives you y and x gives you z. Why are these not part of the three previous rules that we had? Because you can actually prove these based on the previous rules that we had. So let's take union. Given is that you know x determines y and x determines z. Okay, so these are the two that we know. We can use augmentation to add x on both sides. X is already on this side, so you don't get anything new. So x gives you xy, and here you can add augmentation on rule 2, so I know xz, I'm going to add y to both sides. So xy is going to give me zy. And now I'm going to use transitivity on 3 and 4. X gives you xy, xy gives you zy, therefore x gives you zy. So started with given these two, we proved that the union is correct. Okay, so now that you believe me, from now on you can also use union in order to do proofs. You can do a similar thing for decomposition. Decomposition starts with x gives you y and z. We can use reflection, so we know if y and z is true, y is true, and we know that if y, z is true, is also z is true. Now I'm going to use 1 and 2, x gives you yz gives you y, therefore x gives you y. And I also know 1 and 3, x gives you yz gives you z, therefore x gives you y. So given x gives you yz, you can prove that x gives you y and x gives you z. Alright, so what you can do is you can use the 3 rules we had previously plus these two to come up with new functional dependencies. Any questions? Okay, so let's have a look at an example. Suppliers supply parts to a project. Okay, so I have S name, the name of the supplier, the city where the supplier is coming from, and the status of the supplier. Supplier attributes are S name, city, and status. And I also know part attributes. I have a parts number, and I have a part name. I also know the quantity of how many of that part I want. Okay, so I have a supplier, I have a product, and I know the quantity of that product. And these are the functional dependencies that I have. I know that S names gives you city, so I know S name gives you city. City gives you status, product number gives you P name, and S name and product number give you quantity. What I want you to do is to prove that S name and P sharp together is a supergroup. Right? So if you thought using these rules were easy, now is your chance to show that, or to find out that it's not easy.
Something is okay, show that.
Okay, so please use these 3 and also union and decomposition. Raise your hand if you're totally lost, and we can come around and help you guys.
It's one of the minimal keys. It cannot be. Yes.
And now we have estimated status. So we have city status.
Can someone just tell me what it is that I need to show in order to prove that this is a superkey? Yes?
The S name and key number is the minimal key.
That it's the minimal key? Well, I'm just trying to prove that this is a super key, right? See now?
That by knowing S name and P number, you can uniquely identify the other ones.
So I need to prove that if I know S name and P number, that functionally determines all of the attributes in that table. Right? So this is the rule that you're trying to get to. You're trying to prove that S name and P number functionally determines S name, city, status, P number, P name, and quantity. If you can do that, then that proves that this is a super key. Question?
Oh, it's not a question.
It's not a question. Right? Keep going.
Let me write out the whole.
You can't split it up, but I guess it's
But yeah, you just repeat that over and over until you get all of
You're given S name and city, so you can combine that with S name and status. S name and city status. Combine that with this. You got it on 12. I guess, yeah, that works. I just wrote out one side. Here, give it
Is anyone done?
Oh, we're giving it augmentation is you add the same things on both sides. So you can't just skip it. Well, I guess you could. Like, you know that it's right. That's the status. So I think that's one of the rules as well. So you do have to use that. Usually the example we don't ask you list the names that you use, we just ask you. So you don't have to.
So that's using reference. So for each step, you need to do one of those. So the subset could be Right. So let's see. So S name and P number can give you S name and P number by reflection. S name gives you city. You have this from the first functional dependency. You can take this S name gives you city, and the second functional dependency, city gives you status. And with the two of them, with transitivity, you can prove that S names gives you status. Okay? You can take S name and P number and use augmentation to add P number to both sides and on rule 2. So I'm taking this rule, I'm using augmentation, I'm using P number on both sides. So now S name and P number gives me city and P name. And I can take rule 3 and augmentation to say that S name and P number is giving me status and P number. Any questions so far? Okay, so rule 6 is now going to say take rule 1 and rule 5 and take the union of the two. So now S name and P number is going to give me S name, P number, and status. Take the union of 4 of 6, you can also get city in. Now I'm going to use union with the functional dependencies that I have on 7 and 8 to prove at the end that S name and P number is going to give me everything. Right, so this is a proof. A proof would mean that you would even state the obvious ones. Because there's no thing such as obvious, you just have 5 different rules and you're trying to use those 5 rules in order to come up with this proof. Yeah?
If we will be given this question in the exam, will you provide something like the table with the name of those rules? At least the name of the rules?
The name of them, I don't know. It's a short answer. You need to know the rules. So, reflection, you need to know that a subset of what you have gives you that. Transitivity, you need to know. Union, you can write them out yourself if you find it helpful, if you have the rules by your side, but you should know them. Okay? Yes?
For union, can we save time and write all of those in one line so that we don't have to keep union?
So, if you want to do that, then in reality what you need to do is first prove that the union can extend to more than 2 values. So you can have x1 to xn and prove that you can take the union of all of those. But the union that we know how to use only takes 2 values in union and makes the union of those. So the main reason why we're doing this exercise to show you that this is actually not an easy way to do proofs, right? And although I might ask you answer questions on this, but basically in reality, we hardly ever want to do this. There's got to be easy ways that we can do this. All right, let's take a quick break. Let's resume at 25 past.